Greetings and salutations, magical chemists. Today we're going to talk about Le Chatelier's principle, which helps us determine the effect of a change on an equilibrium system. For Le Chatelier's principle, we talk about a change as a stress being applied to the system. Well, if you stress or change a system, Le Chatelier's principle says that equilibrium will shift in the direction to help partially relieve that stress. However, it is important to note that nothing can ever completely reverse the effects of the original stress or change. Right? Let's consider a generic equilibrium system where reactants are turning into products and products are turning into reactants. But because we're at dynamic equilibrium, it's happening at exactly the same rate. Now, let's mess with the system. Let's go ahead and increase the concentration of a reactant. Once you did that, you're not at equilibrium anymore. So to reestablish equilibrium, the system has to use up some of those added reactants, which means it's going to shift to the right and make more products. If you take a system at equilibrium and instead increase the concentration of a product, well, to undo that stress, the system is going to need to shift left to form more reactants. And it's also the other way around. If you decrease the concentration of something, the reaction will shift in that direction in an attempt to replace it. If you decrease the amount of products, the reaction is going to shift right to make more products. If you decrease the amount of reactants, then the system will shift left and make more reactants. So equilibrium position will change to basically try to undo whatever the stress was. Now, it is absolutely essential to note that all of these shifts left and right to reestablish equilibrium, all these stresses by changes in concentration, they are not going to affect the value of your equilibrium constant K. The equilibrium constant is a constant. Well, at constant temperature, that is. Okay, let's take a look at an example reaction. This is about as generic as you get. A plus B react to form C plus D. So let's look at the stresses that you could apply to the system and predict what effect that would have on the equilibrium position. Well, if you add A or B are reactants. The system wants to shift to use up the reactants, so it is going to shift to the right. Of course, if you actually remove A or B, the reaction system will shift left to replace it. Okay, you should go ahead and predict what direction the reaction will shift if you either add or remove C or D. So take a moment and unpause the video when you're ready to check. Well, C or D, they're both products. So if you add extra products, the reaction will shift left to use them up. If you remove products, the reaction will shift right to make more. Okay, so now let's start getting a little more specific. Let's use an actual chemical system. Ooh. We are going to use the classic equation of taking nitrogen gas and hydrogen gas to form ammonia. And the question says, well, what will happen to the equilibrium system above when the following stresses are applied? Let's see how this works. If this system is at equilibrium and you stress it out by dumping in some extra N2, a reactant, hopefully you can see that the system will have to shift to the right to use up the added reactants and reestablish equilibrium. So when you're answering a free response problem, you have to include these three components. You say what direction it's going to shift, why that shift will actually counteract the change, and what the aim is. Luckily, the aim is always to reestablish equilibrium. Remember, a chemical system will always seek the state of the lowest Gibbs free energy, and that is equilibrium. Okay, now you're going to try the same thing, but you are going to attempt to describe what happens to the system if you add in some delicious NH3. So go ahead and try this on your own, and when you're ready to check, unpause the video. In this case, the system will shift left. Why? Well, to use up some of the added product. And with the goal of course, getting back to equilibrium. All right, hopefully this is starting to make a little bit of sense. Even if it's not, I still want you to try both. Yes, both of these last two examples. See what happens, and when you're ready to check, unpause the video. Well, part C, adding more H2, is exactly the same effect as adding more N2 because it's a reactant. So the system will shift right to use up some of the added reactants and reestablish equilibrium. For part D, if you're removing some of your product, well, the reaction is going to shift right to replace it and reestablish equilibrium. So that's the basics of Le Chatelier. However, there are more changes we can make than just changes in concentration. We can also change the temperature. And what's interesting about changing the temperature is if you remember thermochemical equations, you can actually write heat as a reactant or a product. So you can treat a change in temperature like a change in concentration as long as you think of heat as a reactant if it is, oops, those are flipped, endothermic, or product if it is exothermic. Let's consider exothermic reactions first, where heat is produced as part of the reaction. Well, since heat is a product, if you increase the temperature, it's like you're adding more of a product. So what will the reaction do? Well, it's going to shift left to use up some of that added product, that added heat. Well, if you decrease the temperature and make it colder, the system is going to shift right to replace some of that heat that was removed. But here's the crazy part. Remember how K is a constant, but it's only a constant at constant temperature? We just changed the temperature. So in this case, when I increase the temperature of my exothermic reaction and the system shifted left, making more reactants, K will actually decrease in value because we have less products at equilibrium. But decreasing the temperature, causing the reaction to shift right, K will actually increase because there will be more products at equilibrium. And in an endothermic reaction, well, everything is the opposite because heat is a reactant. That means increasing the temperature will cause the system to shift right, whereas decreasing it will cause it to shift left. And because we've changed the ratio of products to reactants at equilibrium, the value of K will actually change. So notice, this is so important, so break out your highlighter, whatever you do to make sure you know this sentence is important. But only a change in temperature will change the value of K, no matter how the reaction system shifts. Okay, let's try a couple practice problems to see what you might be asked about Le Chatelier relative to changes in temperature. Okay, so this first question gives you a generic equilibrium system, and it says, well, what happens to the system above if your temperature is decreased? Whenever you see a change in temperature, your brain needs to be like, wait, is heat a reactant or a product? Is it endo or exothermic? That's the very first thing you have to answer. Well, looking at this delicious thermochemical equation, you'll notice that heat is a product. That means decreasing temperature is the equivalent of decreasing the concentration of a product, so the reaction will shift towards the products to replace some of the heat removed. In a free response explanation, it is absolutely key that you identify that the reaction is exothermic. Or you could just say, because heat is a product. One of those two things has to be stated before you give your answer. Okay, so you've identified that the reaction is exothermic, or you've said heat is a product. So then we're allowed to say, well, therefore decreasing temperature will cause the reaction to shift right. Or you could say shift towards products. Either are equivalent. And then finally you have to say, but why? Well, we want to replace some of the heat removed and reestablish equilibrium. Okay. If they had only asked us what happened to the equilibrium system, we'd be done. But there was a second question. They said, what happens to K, your equilibrium constant? Well, since we know what direction the reaction shifted, shifting right will increase your products and decrease your reactants, increasing the value of K. Okay, I know this looks a little bit messy, but I wanted to make sure you knew that you have options for your explanations. One of the things that I am always asked for these Le Chatelier questions is, do I have to actually say, according to Le Chatelier? And the answer is no. which is good because honestly, Le Chatelier is kind of hard to spell. So you're allowed to simply talk about the cause and effect. Decreasing the temperature causes the reaction to shift right because it was exothermic, therefore increasing concentration of products, therefore increasing value of K. All right, I swear this will become, basically the pattern of what you have to say will become more clear as we continue to practice. Now, the next question, I think, is a little more interesting. So why don't you take a moment to read through this lovely problem and see if you can come up with an answer to the question. When you are ready to check your answer, go ahead and unpause the video. Okay, first let's parse what's going on in this problem. The reaction of what's happening is kind of buried within the equation, but they're mixing nitrogen and hydrogen gas to form ammonia. That seems to happen a lot. Notice that they are specifically doing this at 773 Kelvin. And when equilibrium is established at this temperature, this specific number of moles of NH3 is present. However, they do the same reaction again at a lower temperature. And when they do that and equilibrium is reestablished, well, in this case, you actually have a lot more NH3 at the colder temperature. That means decreasing the temperature, aka removing heat, caused the concentration of NH3 to go up. This means removing heat caused the concentration of products to increase. So if you haven't yet, take a moment and decide, is this reaction endothermic or is it exothermic? And see how you would justify that. And of course, if you've already tried it, then we'll go ahead and go over that in just a moment. Did you see that the reaction must be exothermic? Let's see how we would justify that. First, we just identify the pattern that we noticed. Well, decreasing the temperature caused the reaction to shift towards products. And then you're going to say, how did you know that? Well, it's because the number of moles of NH3 increased, which means heat is a product of the reaction. Okay, changes in temperature are probably the most complicated forms of Le Chatelier shift because they actually affect the value of K. But there are actually other changes you can make, other stresses you can apply to the system. How exciting. You can change the pressure or the volume of the system. But please note, these changes will only affect equilibrium systems that actually have gaseous reactants or products. Basically, if you have a gas, changing the pressure or changing the volume is the equivalent of changing the concentration. So you can follow the same logic that you would use when you're looking at Le Chatelier shifts for concentration. If you increase the pressure of a gaseous system, in that case, the system wants to shift to decrease pressure. So it's going to shift to the side with fewer gas particles. Decrease the pressure? Well, we want to undo that. So the system will shift to the side that has more gas particles, partially increasing the pressure back to reestablish equilibrium. What's interesting is that the system has equal numbers of moles of gas on both sides, well then changes in pressure or volume will have no effect. One more interesting thing to note. If you add an inert or non-reactive gas, that actually does not affect the location of equilibrium either, since the partial pressures of the gases in the reaction wouldn't be changed. When you're considering changes in volume, just remember that whatever you did to volume did the opposite to the pressure, and then you could just still think about it in terms of pressure. So if you increase the volume of a gaseous system, well, you've given it more space, that decreases the pressure, so it's going to shift to the side with more gas particles. It's got space for more. And of course, the opposite. If you decrease the volume, it doesn't have as much space, so to reestablish equilibrium, it will shift to the side with fewer gas particles. But of course, as long as you are at constant temperature, changing the pressure or volume will not affect the value of your equilibrium constant K. Okay, before we try some practice problems, I want to point out one more thing they like to throw at you sometimes as a trick question. They say, what happens to equilibrium position if you throw in a catalyst? Well, as you might recall from kinetics, a catalyst is something that increases the rate of the reaction by lowering the activation energy. But that has absolutely no effect on the equilibrium position. Technically, adding a catalyst will increase the rate of both the forward and the reverse reactions equally. So you'll reach the lowest energy state more quickly, but equilibrium will still be in the same place. Okay, let's go ahead and try a practice problem that ties all of this information together. So we're going to be looking at an exothermic equilibrium system. Now, whenever they say it's exothermic, I have to admit my first instinct is to go ahead and add heat into the reaction so I know if it's a reactant or product. In this case, exothermic means heat is being produced. This question is a little different than the other ones we've done because it just wants you to predict how each of the following stresses will affect the concentration of O2 and the value of K. But you don't have to justify. Ooh, exciting. You're just trying to predict what's going to happen. So I would like to do a couple of these with you together, and then you can try the rest on your own, which will be ever so much fun. I would like to look at C and D with you together, and then you're going to go ahead and try the rest of them on your own. So remember the idea here. It says for in C, you have halved the volume. You've basically made the container smaller. If you change volume or pressure, the first thing you need to do is figure out, well, are there even anything that's going to be affected? Do I have gas particles? Well, yeah, turns out this entire system is made out of gas particles. Then you have to figure out where the most gas particles are. Like, how many gas particles do I have as the reactants? How many as a product? Well, it turns out you're literally just counting. I've got 2 NO2 gas particles as a reactant, so I'm starting with 2 gas particles on the reactant side. But on the product side, I'm producing 2 O2 particles and an N2 particle for a total of 3 gas particles. The reason this is so important is we just cut the volume in half. We've decreased the space available. So that means to reestablish equilibrium, we have to shift towards the smaller number of gas particles. Well, in this reaction, there are fewer gas particles on the reactant side, so we are going to shift left as a result of the stress. Now we have 2 questions to answer. We want to know, well, what does that do to the concentration of O2? Well, you're shifting towards your reactants, but O2 is a product. That means the concentration of O2 will decrease. However, the temperature was constant. That means K is unaffected. The only part of this that was actually asked for in the question is just identifying what happened to the concentration of O2 and to K. However, the rest of it is me making sure that it makes sense. So let's try one more together, and then you can try the rest on your own. In part D, helium gas is added. Well, we're just going to see, did we add a reactant or a product? But wait, helium's not even in the reaction. Like, what the what? I don't get chemists. They're weird, right? Well, helium is a noble gas. That means it is an inert gas. And that means it doesn't matter that you've added it because it's not actually going to affect your equilibrium position. That means in this example, both the concentration of oxygen gas and K remain exactly the same. All right, it's your turn. You have, let's see, I guess there are 4 more left. And yes, I would like you to try all of them. When you are ready to check your answers, unpause the video. For part A and B, increasing the reactant or decreasing the product is actually going to have the same effect. Both will cause the equilibrium system to shift right, increasing the concentration of oxygen gas, but constant temperature, so K is unchanged. Speaking of temperature, in part E, we've increased the temperature, which for this system is basically equivalent to increasing the amount of a product. Thus, to undo that stress, the reaction is going to shift left. That will decrease the concentration of O2. But that's not all. We have changed the temperature. So the equilibrium constant K will actually change. In this case, you've decreased the concentration of products at equilibrium. You decrease the value of K. Last but not least, you added a catalyst. Classic AP trickery. But a catalyst just speeds up the forward and reverse rates. It does not affect your equilibrium position. So there is no shift and thus no change in the concentration of O2 or K. Okay, Okay, indeed, right? Lots of equilibrium constant K. So that is the basics of Le Chatelier. There is, however, one more page I want you to take a look at. So this is kind of a concept map that I found on the internet and stole because it's awesome. And it basically is showing you what happened, like what Le Chatelier's principle is talking about. You're always starting with a system at equilibrium if you're doing Le Chatelier. And equilibrium, your Q is equal to your K, your delta J is 0, your delta G is 0, free energy is at a minimum, right? But then, stress. Oh no, the system is not happy, right? Nobody likes stress. So then Q and K are not equal anymore. And the reaction is going to shift until equilibrium is reestablished. And that's the idea. So thank you for playing with the glories of Le Chatelier and, of course, delicious chemistry.